Dear students, welcome to the next lecture on inorganic chemistry. We shall continue our discussion on group 17 elements. The halogens form hydrides of the formula HX. X2 plus H2 gives 2 molecules of HX. And these are acids which ionize in aqueous medium to form H plus and X minus ions. The acid strength follows the order HF less than HCl less than HBr less than HI. So as the size of the halogen increases, the acid strength increases. We know that the electronegativity of the halogen decreases from fluorine to iodine. So fluorine is most electronegative, and thus the polarity of HX bond decreases from fluorine to iodine. That is, in HF the bond is most polar and the HI bond is least polar. So we will expect that HF is the strongest acid. But the acid strength depends not only on the electronegativity of the halogen and the polarity of the bond, but also on the bond dissociation energy. The bond dissociation energy decreases from HF to HI. This is because of the large size of the iodine. Effective overlap of iodine and hydrogen is not possible as in the case of HF. Iodine, the HI which has the least bond dissociation energy, is the strongest acid. When the bond dissociation energy decreases, the dissociation of HX to form H plus and X minus becomes more easier. And thus HI is the strongest acid. When we compare the reducing property, considering the size of the halogen increases from HF to HI. The strength of the HX bond decreases from HF to HI. As the bond strength decreases, thermal stability also decreases, and thus the reducing character increases. Hence HI shows the strongest reducing character. The boiling points of the hydrogen halides are shown here. The boiling points increases from HCl to HI because As the molecular size increases, van der Waals forces increases and hence boiling point increases. HF shows an anomalous boiling point. This is because of intermolecular hydrogen bonding in hydrogen fluoride. Fluorine is highly electronegative. The electronegativity value is 4. HF bond is highly polar and hence there is a possibility of intermolecular hydrogen bonding, and thus the molecule shows a very high boiling point compared to other hydrogen halides. Hydrochloric acid is an important laboratory reagent. In laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. The HCl gas is passed through distilled water to get the liquid form of hydrochloric acid. NaCl plus H2SO4 gives NaHSO4 plus HCl, and if NaCl is present in excess, two molecules of NaCl reacts with sulfuric acid to give sodium sulfate and HCl. Commercially, HCl is prepared by the direct reaction of hydrogen gas and chlorine gas, which are obtained as the byproduct during the manufacture of sodium hydroxide by the electrolysis of NaCl solution. The reaction is exothermic in nature. Delta H is equal to minus 185 kilojoules. Hydrogen is allowed to burn in dry chlorine in a silica chamber to get HCl. The HCl gas formed is cooled by passing through externally cooled pipes and absorbed in water or dilute HCl to get hydrochloric acid. The acid thus obtained is almost of the strength 36%. HCl is used for the manufacture of chlorine, ammonium chloride, etc. It is used for cleaning iron sheets during tin plating and galvanization. HCl has applications in medicine, textile and dyeing industry. It is a laboratory reagent which is used for qualitative as well as quantitative analysis. HCl is used in the preparation of aqua regia for dissolving noble metals and their purification. Halogens form binary oxides of varying oxidation states. For example, the oxides of chlorine are Cl2O, in which chlorine is in plus 1 oxidation state, Cl2O3, in which chlorine has plus 3 oxidation state, ClO2, in which the oxidation state of chlorine is plus 4, Cl2O6 and Cl2O7, in which the oxidation states of chlorine are plus 6 and plus 7 respectively. The molecule ClO2 has a bent structure with both ClO bonds of same length. The bond length is 147 picometer and the bond angle is 117.6 degree. This is an odd electron molecule. And it has a special 3 electron bond and the extra odd electron resonates between two CLO bonds as shown in the figure. Because of the presence of unpaired electron, the molecule is paramagnetic. Even though there is an unpaired electron, ClO2 does not show a tendency to dimerize. This suggests that the odd electron of the 3 electron bond is delocalized over the molecule. Next is the electropositive character of iodine. As we move down the group, the electropositive nature increases and iodine has an ionization energy of 1009 kilojoules per mole, which is less compared to other halogens like fluorine, chlorine and bromine. Solid iodine has a metallic luster. Iodine has a tendency to exist in +1 and +3 states. Iodine monochloride ionizes as two molecules of ICl giving I plus and ICl minus. Iodine phosphate ionizes as I3 plus and PO4 3 minus. These compounds of iodine conduct electricity in the molten state due to the formation of I plus and I3 plus, and upon electrolysis iodine gets liberated at the cathode. The formation of I plus and I3 plus have been established spectroscopically. Also, iodine exists as I plus in coordination complexes of pyridinium compounds of the type IPY twice Z, where Z is nitrate or perchlorate anion. Upon electrolysis of these complexes, iodine gets liberated at the cathode. Acetanilide undergoes aromatic electrophilic substitution when treated with ICl to form 4-iodoacetanilide. This reaction is also a proof for the formation of I plus ion. I plus acts as the electrophile in this reaction. These are the proofs for the electropositive character of iodine.